Hello everyone, and welcome to the video tutorial on forces. Now, in this tutorial we are going to talk about Newton's first law and Newton's second law and how we can apply that to certain situations. So, Newton's first law. It is the, if an object is at rest, it will stay at rest unless acted upon by another force, or an object moving at constant velocity will stay moving at that constant velocity unless acted upon by another force. You can imagine sliding a hockey puck on a table. Now, if I slide it on the table, what's going to happen is friction is going to slow the force or slow the puck down. So if I wax the table, it would slide further. If I put it on ice, it would slide even further because what I'm doing is I'm reducing that force of friction. If I had it on a completely frictionless surface and I gave it a little nudge, then the only forces acting on it would be the force due to gravity and also the normal force. And since the puck would be moving at constant velocity, its acceleration would be zero. So constant velocity implies, again, acceleration is zero, and the net forces on that puck would be equal to zero. So in other words, the puck would be in equilibrium. When an object is in equilibrium, the sum of all of its forces equals zero. Now, forces. You can imagine them as basically vectors. And so say I've got my force due to gravity here, and I've got my normal force here, and then I've got, let's say this is a force due to friction back here, and then I am pulling this little ball across the table. So I am pulling it on a rope, so I've got tension. And let's say I'm pulling the ball so that it has constant velocity. Well, in that case, this tension force is going to be equal to this force due to friction. Well, that leads us right into Newton's second law, which is the most profound law that you'll use on these problems. And it says that the summation of the forces needs to be equal to the mass times the acceleration. So, whenever you have acceleration of zero, then that means that the sum of the forces, the vector sum, must also be equal to zero. That is when you are in equilibrium. Equilibrium. Make that a little taller, shall we? So, equilibrium, the sum of your forces equals zero. Now, this is the vector sum. So, the summation of the forces in the x direction must be equal to the mass times the acceleration in the x direction. And the summation of forces in the y direction must also be equal to the mass times the acceleration in the y direction. So, Newton's second law. This is your bread and butter for problems involving forces. Now, let's do an example where, let's say we've got, let me scroll down a little bit. We've got a block, and it is attached to the wall with this cable. Let's call this T1, and then it's got another cable, T2. It's attached to the ceiling. And let's say this block weighs 10 kilograms. Okay. Now, in this problem, the block is suspended. It's in equilibrium. In other words, its acceleration is zero. So that means that the sum of the forces in the x direction equals zero, and also the sum of the forces in the y direction equals zero. So, with these types of problems, it's beneficial to try and see the forces as a coordinate system. So see the vectors as if you have an imaginary coordinate system running through, where you've got the y as your up and down and your x as your horizontal. Now, the forces that are acting on this block, you've got these two tension forces, but you've also got the force due to gravity. So, let's start with the x. The summation of my forces in the x direction, again, equals 0. And that equals. Now, let's look at the forces in the x direction. I've got T1 as is. So T1 is a force that I have in the x direction. My gravity is going straight down. My force due to gravity is going straight down. So it only has a y component. My other x component is going to be the x component of this T2 force. Now, like so. Now, let's say this is at some angle theta. Okay? Some of the forces, if we treat this as a traditional coordinate system, then that means that the T1 is going to be in the negative x direction, and this T2x up here is going to be in the positive direction. So the sum of my forces becomes T2x minus T1. Now, what is T2x? Well, we can use this angle, and this is the adjacent to that angle. So my x becomes, or T2x becomes, T2 cosine of theta. So now I can take this and plug that in. So I've got 0 equals T2 cosine of theta and then minus T1. Those are all my forces in the x direction. So now I've got two unknowns here. So now let's look at the summation of the forces in the y direction. And again, this equals 0. So now let's talk about our forces in the y direction, our up-down. I've got my force due to gravity, which is in the down direction. So I'm going to make that force negative. My other positive y component of force is going to be the y component of T2. And so to get that, to get T2y, T2y is going to be sine. So we've got T2 sine of theta. So, summation of my forces in the y direction, T2 sine theta minus the force due to gravity. Well, the force due to gravity is going to be mg, so I've got 0 equals T2 sine theta and then minus mg. Now, I've got two equations and I've got two unknowns. So depending on what your problem is, say we're looking for T1. They want to know the tension in T1. Well, what I can do is I can pick an equation that's easiest to solve for. This one is the only one that involves T1. So what I need to do is solve for T2 over here, add mg to both sides. So I've got mg equals T2 sine theta. Divide by sine theta on both sides, so I've got T2 equals mg over sine theta. Take that and plug it in for T2. So I have 0 equals, now I've got mg over sine theta times cosine theta, and then minus T1 equals 0. So I can add T1 to both sides. And cosine over sine is cotangent, so cotangent theta. Now, that would be as far as I could go because I'm not given this angle. Okay? So, that would be as far as you could break down this problem to solve for T1. So, that is how to best go about a problem like that. Break up your forces into components and vectorially add those forces to get the proper force, the summation of forces that you need. So if my body's not accelerating, then the summation of my forces needs to equal 0.